Hello, everyone. I'm going to go over some important notes for the electrochemistry experiment that you're about to view, and then the lab report for the lab report you're about to write, and also just go over some pre-lab information for you for this experiment. Okay, so let's go ahead and get started here. On a couple of notes, you should go ahead and review the determination of oxidation states and some other things that you probably are already learning about in class. But it'd not be a bad idea to go ahead and review them. I'm not going to do that in this pre-lab lecture. And then you probably are also learning about redox reactions. I guess you could say I'm going to go over a little bit about that because I'm going to go over some information about half cells. In the experiment, you're going to view a couple of different half cells and half reactions and determine their potentials. So you're going to need to balance some half reactions. You're also going to determine some potentials from those half cells, and also going to connect them in parallel and in series and see what that does. So let me give you a couple of important pointers for doing those calculations and for what you're about to view. One reaction is always going to give electrons and the other one is going to take electrons. So one of those is going to be the oxidation and one of those is going to be the reduction reaction. We compare these guys to the standard hydrogen electrode cell. This is because the potential has no meaning in and of itself. We must compare it to a reference point. So this would be the same as if we compared everybody's height to one standard height, like say 5'10", and then we just measured you and you're either taller or plus or shorter, negative to that standard height. That's kind of what we're doing with the standard hydrogen potential of the standard hydrogen cell. Okay, so when we write these out, the standard form is to write them as a reduction reaction, so that you say the standard reduction potential of this particular reaction. And then they'll draw the electrons in there, and then they'll give you a little delta E cell is equal to some number of volts. I'll show you some examples here in just a second. So the reduction, all right, means that we are adding electrons to it. Now, when we form these into a battery, one's going to be oxidation and one's going to be reduction. So one of those is going to have to be flipped around in order to make the oxidation reaction. So reduction gains electrons, oxidation loses electrons. And just a reminder, at the cathode, all right, reduction. Reduction takes place at the cathode and then oxidation at the anode. So a little acronym to help you remember that. An ox and red cat. So at the anode, oxidation, and then reduction at the cathode. Okay. All right. And then we can add these standard electrode potentials together to make something like, say, a battery. So if we combine one as the reduction and one as the oxidation, then one guy's going to be giving electrons, the other guy's going to be taking. We can then utilize that electric potential, right? We just capture it sort of and run a line connecting the two, and then sort of put something in between that line. So we use that energy. And this is the principle behind batteries. Okay, so let's look at an example here. And I'm going to give you just a different example from exactly what's in the book. Copper is the same, but I've used a different potential for iron here that's not in the lab notebook. So let's say we wanted to put these together and form a battery out of them. All right, so we go to a book and we look up the standard reduction potential. So you can see it's a reduction because in this case, the copper 2+ ion is gaining 2 electrons to make just copper solid. Okay. On the iron side, however, we note that it's going from a oxidation state of 3+ to 2+. So we just start getting 1 electron from this. When we balance half reactions, we need to make sure that the number of atoms, but also the number of electrons is balanced. All right, so let's go over a couple of notes on what we're doing there. And also just what we do with forming these into the batteries and finding the potentials of the cells. Okay, so we're going to need to reverse one of these. The one that we're going to reverse is the copper. So we're going to make copper the oxidation. Remember your acronym here, anox and a red cat. So if we make copper, the oxidation reaction, then we know that's going to be the anode. All right, so we know which electrode each of them is, and we know which one's oxidized and which one's reduced. Once we get the reaction balance, and we can see the two electrons are going to cancel out from the overall reaction equation, and then after we just need to add together the two electrode cell potentials. Remember, in order to get the electrons to balance, right, the way it's written right here, these electrons are not balanced. In order to get it to balance, we need to multiply the iron half reaction by 2. When we do that, because I had to edit this video because I made this mistake, I was thinking it was like enthalpies. We leave the potential the same. So even though we multiply the reaction by 2, it does not change the voltage on the cell potential. So we take our two half reactions. They are all completely balanced. We have changed the sign on the copper electrode. It was positive, and when we reversed it, it became negative. And then the overall reaction is what we want. And then the cell potential, we just add together these two. Okay. All right. And then part 3, we're going to do a little bit with connecting these, a couple of different types of batteries or galvanic cells or voltaic cells in series and in parallel. And when we do this, we see that some kind of weird things happen with the potentials and the overall battery capacity. So if you connect batteries in parallel, you're going to maintain the same voltage. All right. However, your overall capacity is going to add together, right? So same voltage, but the overall capacity increases. You can kind of think of this. This is just an example that I came up with here. Is kind of like as if you get the same horsepower, but the number of miles that you can drive with the car increases. Okay, so kind of like maybe increasing the amount of gasoline or something like that. However, a different thing happens when we connect them in series. So when we do this, we add together the voltages, but you have the same overall capacity for that. So you can kind of think of that as now your horsepower increases, but you can only travel the same amount of miles, right? So in parallel increases like your mileage, and then in series increases your horsepower. Okay. So some notes about the actual experiment. You will see in there that we got some wonky values in part 3 in particular. And I want you guys to just assume that those are that's the data that you got, and use that data. It's okay that it's kind of weird. So use that data, and then you're going to take that data and perform some calculations. As long as you do the calculations with the data correctly, that's fine, and you're going to do some analysis. When you do the analysis, you'll then determine, the percent error, and you can look at it. Did you get, relatively speaking, good or bad numbers from it? And it's going to be a little bit off. I'm just telling you that, but that's okay. All right, you just want to use that and move forward with it. Okay, so that is it, and good luck on the experiment.